and figure out force on a wire in a magnetic field. This is sometimes referred to as the motor principle. Okay, so first of all, to understand it, we have to understand what two magnets sitting next to each other do to each other relative to their magnetic fields. If I've got a north and south bar magnet side by side here, and I'm interested in what they do to each other, we know since the opposites are near each other, they're going to wind up attracting each other. My magnetic field comes out from the north, and we're just going to draw them isolated, each magnet by itself, into the south, and I'll put a little line right here. Out from the north, into the south. And if we take a look at the magnetic fields where they interact between each other, they are in opposite directions. Look at these guys. Out from the north, into the south, out from the north, into the south. We have like poles near each other, so they're obviously going to be repelling each other. And right in between, the magnetic fields are in the same direction. Okay, keep that in mind. Magnetic fields in opposite directions cause the bodies to want to move the fields into each other and attract. Magnetic fields in opposite directions are going to cause repulsion. Now let's picture over here a wire sitting between two ends of maybe a big horseshoe magnet or whatever it might be. You've got a north and a south pole here. And we want to find out what direction is that wire going to get a force on it. Well, first, let's draw the magnetic field going around the wire. Current is coming out of the page. Thumb points out, fingers wrap around, so I'm going to get a counterclockwise magnetic field going around that wire. So let's do this. Here we go. It's going to come out, around like this. Go here. It actually goes behind the wire there and comes out and goes around in that direction just like that. So it's going up, beyond, up and around like that. Okay. Now let's picture the interaction between the two magnetic poles here. I'm going to get a magnetic field going, external magnet, from the north to south pole. Bam. I'm going to wrap this, just bend it a little bit because we don't want things to cross. The fields do not cross. There. And then we're going across like that. Bam, bam, bam. Good. There we go. We've got our arrows all drawn in. Now let's look at where these two fields are going to interact with each other. Down below, we have got magnetic fields in the same direction. So we know that they're going to repel each other. So these guys are trying to do this. They're trying to push apart. They're trying to move the wire up and the magnets down. Action, reaction. The wire gets pushed up. The magnets get moved down. Most of the time the magnets are fixed. So you don't see the wire move. But action, reaction works. Keep that in mind. On the top here, I've got my magnetic fields in opposite directions. And since they're in opposite directions, they're going to attract each other. So now on the top, they're trying to pull into each other. It's trying to lift the wire up and pull the magnets down. Well, both of these are generally trying to do the same thing. The lower part over here where the two fields interact is trying to push the wire up. And on top, it's trying to pull the wire up. And of course, push the magnets down, which means that wire is going to get a big force in that direction towards the top of the page. Notice that the force is perpendicular to the magnetic fields that the wire is sitting in and perpendicular to the current. Let's flip over to the next page. In order to find out the direction of the force of a current carrying element, a wire, that's sitting in an external magnetic field, once again, we use a right-hand rule. We'll take our hand, and your hand needs to be held flat with your fingers perpendicular to your thumb. Now, if you think about it, there's some nice analogies here. You've got one wire carrying current. You've got one thumb on your hand. Your thumb is going to point in the direction of the current. There's lots of magnetic field lines, so you've got lots of fingers. Your fingers aim in the direction of the magnetic field. I'll just put a B there for magnetic field. And the part of your hand you would push with, the palm of your hand, if you could picture an arrow coming straight out from the palm of your hand, that's the direction of the force. So let's flip back onto the other side and just see how well this physically works out. There's my original problem. I keep my hand flat. I rotate it till while my fingers point in the direction of the magnetic field. My thumb points out of the page, and my palm aims in the direction of the force on the wire. To calculate the force, we're pretty fortunate because the equation just makes sense. Exactly what you think would affect it does affect it. The force is equal to the current times the length of the wire times the strength of the magnetic field multiplied by the sine of the angle between the magnetic field and the current. This means that 90 degrees is going to give us maximum force. 0 degrees is no force. If the current's parallel to the magnetic field, you're not going to wind up having any force on it. Now, if I took a look at this, let's take the problem that I've got down here below. If I want to determine the direction of the force on the wire, I can look at one of two ways. I could say, all right, I'm only interested in the direction of the current that's perpendicular to the wire. So there would be the direction for my current that's perpendicular to the wire, and I could do a hand rule. Fingers point in the direction of the magnetic field, thumb points in the direction of the current, and it's out of the page. Or, if I wanted to, I could look at it a little differently. I'm just going to redraw it over here. Raise it up a little bit. My magnetic field lines. Okay, here's my wire. The other way I can look at it is I could take the part of the magnetic field that's perpendicular to the wire. I'm going to get exactly the same results. In this case, hands held flat. There's my fingers pointing in the direction of the component of the magnetic field perpendicular to the wire. And my thumb points in the direction of the current. It's still, in both cases, the force is out of the page. Now, there's some problems here I'm going to post. I would like you guys to please do those problems. They're not very tough, okay? But I would like you guys to please do those.